So hi everyone. So this is the second part in our series of 3 parts, or probably 3 parts only, for discriminant function analysis. And in the first part, I taught you about the data set. We were also done with, performing the analysis, the steps, but I made you interpret the output till this point. Okay, so till the correlations between the independent variables. Now we're going to move to here, boxes test of equality of covariance matrices. Okay, so just a quick recap: dependent variable is purchasing a bike or would not purchase a bike, and independent variables are 3 attributes in the bike: durability, uh, performance of the bike, and looking of the bike. Okay, so boxes test of equality of covariance matrices. So this particular test is necessary to justify one of the assumptions in discriminant function analysis. So that assumption says that the variance covariance matrices should be equal. Okay, so for particularly boxes test, you could write down the null hypothesis if you're taking it down. So null hypothesis is that the population covariance matrices are equal, and alternative is that the population covariance matrices are not equal. And for us, what is desirable? The null hypothesis is desirable. So let's see in this boxes M, what is the p-value? The p-value is 0.062, which is greater than an alpha of 0.05. That means I'm not able to reject the null hypothesis, and that is something which is desirable also. So I can say that my assumption of equality of covariance matrices is met. Okay, so boxes test has allowed you to accept the null hypothesis, and in a way you're saying that the population covariance matrices in your data are equal. Now, what is this log determinants? Log determinants is natural logarithm of the determinants taken up for each of the independent variables. So not going into the math of it, but you can visualize log determinants as this, that each of the log determinants should be as, so basically they should be as close as possible for this homogeneity assumption to be met. Okay, so for boxes M test to be justified and your assumption to be met, you should have log determinants for each of the independent variables to be relatively equal. And let's see how it is faring in our data. So we have 16.25, 16.14, 16.54, everything near 16. So because log determinants are relatively similar to each other, they're relatively equal, we can say that our boxes M test should also say the same tone, and that is what we saw also. Here also null hypothesis was accepted. So just alternative way of looking at boxes M. And rank here means the number of independent variables. So we have 3 independent variables. Okay, so coming on to the summary of canonical discriminant functions. Okay, before that, please take it down that in discriminant function analysis, your boxes M test is highly sensitive if the normality assumption is not met. So basically, if your independent variables are not normally distributed, your boxes M test could show you otherwise. So the assumption will not be met. Okay, but even if, so I'm saying that even if the boxes M test is not justified, you could still go with your discriminant function analysis, provided the data does not have very significant outliers. So outliers is a way bigger problem. Okay, so that is also something you need to be wary of, you need to be careful of. Okay, so coming on to summary of canonical discriminant functions. So here eigenvalue, so eigenvalue means that the larger the eigenvalue, the more of the variance in the dependent variable is explained by that particular discriminant function. So keep it in mind that in discriminant function analysis, your output is going to give you a lot of discriminant functions. So basically the objective is to come up with discriminant functions, but how many? So the number of discriminant functions is the number of categories in the dependent variable minus 1. So here in my data set, I have 2 categories in my dependent variable. So I will have 2 minus 1, that is 1 discriminant function obtained. So from this data set, I will get 1 discriminant function. However, if you had more than 3 categories, more than 2 categories in your dependent variable, you could have more than 1 discriminant function. Okay, and each of the function has its own explanatory power. Okay, and you choose the function which has the best explanatory power, and it's usually the first one. Okay, so as you can see, function means that you have just one discriminant function obtained. Eigenvalue represents the percentage of variance which is explained in the dependent variable by the discriminant function. Mind it. Okay, so that is coming over here 100. So that means 100% of variance in the dependent variable is explained by your discriminant function so obtained. Okay, now you can always look at eigenvalues in a fashion that larger the eigenvalue, more of the variance in the dependent variable is explained by that function. Okay, and when you'll have more than one function over here, so we'll do that in more than 2 groups discriminant analysis, you will see that eigenvalues are sorted in descending order. So the most preferred function would always be at the top. Okay, as percentage of variance will be also in the decreasing order. Okay, so that was about eigenvalue, and as I said that a larger eigenvalue is associated with a stronger function. So this in a way conveys the importance of discriminant function. Okay, so the discriminant function your data is giving you, how important it is being given by this eigenvalue, and there is no upper limit to what value eigenvalue can take. Okay, so you have to be careful. So better look at this percentage of variance. Okay, now coming on to the Wilks lambda. Wilks lambda is just the opposite of eigenvalue. Okay, and how come? I'll tell you that. So it indicates the proportion of variability in the dependent variable not explained by the discriminant functions. Okay, so Wilks lambda is clearly the opposite. So you can say that if eigenvalue is goodness of it, Wilks lambda is badness of it. I would rather learn it as like this: W for Wilks, W for which. So nobody likes witches, so we can say that Wilks lambda conveys the badness of it in your model. So what is desirable? A lower value of Wilks lambda. Okay, so mind it that closer is Wilks lambda to 0. That means more important is your discriminant function. Fine. I would like to at this point also explain the Wilks lambda which we came across in this output. Okay, the test of equality of group means. I did not explain Wilks lambda in my earlier lecture, so I'm explaining it now. Here Wilks lambda will indicate the proportion of variability not explained by that particular independent variable. Okay? This one explained the proportion not explained by the function, that is discriminant function. But this one is explaining the proportion of variability not explained by this particular independent variable. Okay, so in a way, this is now going to convey which independent variable is more important to your analysis. Okay, so the lower the Wilks lambda, the better it is. So let's see, for durability, we have the lowest, it is 0.432. That means durability as an independent variable does the best job among all the independent variables in explaining the variability on the dependent variable. Okay, and then secondly, we have performance 0.67. Lastly, it is the looking of the bike. Okay, so looking of the bike is not doing a very good job in explaining the dependent variables variability. Okay, so this particular Wilks lambda is telling you that which independent variable contributes significantly in the discriminant function analysis. Okay, so coming on to our Wilks lambda obtained for the discriminant function. So this Wilks lambda is telling you the importance of this function now. Now there is a chi-square test here. So the null hypothesis for this chi-square test is that functions have no discriminating ability. Okay, so the discriminant function which you have come up with here, that this discriminant function has no discriminating ability. So is that desirable for you? No. You want your discriminant function to do the best possible job. You want it to discriminate as best as possible. Okay, so what is desirable now? You want to reject this null hypothesis, and we see the corresponding p-value is 0, which is lower than alpha of 1% or 5%, and therefore we reject the null and say that, okay, my corresponding discriminant function does a good discriminating job, and also it explains the group membership well. Okay, so that was about the Wilks lambda and eigenvalue, both of them being exactly opposite to each other. Next, we come on to the standardized canonical discriminant function coefficients. Now, you will get two discriminant function coefficients. One will be the standardized one, another will be the unstandardized one, as you can see in the canonical table part. Standardized means something like a standardized regression where you have coefficients standardized using the variance. Okay, so standard deviation element is there. But unstandardized means your raw betas, the usual regression which you do. Okay, and this particular coefficient is nothing but your coefficients in the discriminant function. What is your discriminant function? It is something like di is equal to alpha plus beta 1 x1 plus beta 2 x2, where your di is the dependent variable, that is the groups, and x1 x2 are your two independent variables, for example. So in this particular discriminant function, I am getting two different coefficient results. One is standardized and one is unstandardized. Okay, so let's first look at the standardized canonical discriminant function coefficients. Okay, so these serve the same purpose as the beta weights in multiple regression, just that these are standardized. Now they will indicate the relative importance of that independent variable in predicting the dependent variable. So they allow you to put comparison on a common footing because all of these are standardized. Okay, so they allow you to put the comparison on a common footing. That's the benefit of standardizing your data, right? So how to interpret it? The coefficients with a higher size reflects that that particular independent variable has greater discriminating ability. Okay, so likewise we have the highest at durability, then 0.423 at performance, and 0.471 at looking. You have to take absolute values. Okay, so the one with the highest absolute value is more important as an independent variable in discriminating between the groups on the dependent variable. So to us, durability is the best, and then performance, and then looking of the bike. So this is how you get the desirability of the independent variables. Okay, so durability as an independent variable is time and again emerging as the best independent variable. The order is continuing to be the same. Okay, now next we have the structure matrix. Structure matrix in a way now will convey the order of importance of each independent variable. This conveyed the importance. Now this is also going to do the same job. Okay, just that it is going to work by the virtue of something like these weights. We call these as factor loadings. Okay, so the higher is this weight, the more important is that independent variable. Okay, so 0.818 is the highest amongst these. That means durability is the most important independent variable for us. Likewise, next we have performance as the important variable, and lastly looking of the bike. Okay, so structure matrix is giving you an order of importance of each independent variable. Okay, so these particular components, so this 0.818, 0.501 and minus 0.038, what are these? These are called canonical correlation. coefficients. Okay, so basically these are something like correlations of each variable with the discriminant function. Okay, so these convey the correlation between each independent variable and the discriminant function. Higher the correlation means higher is the importance of that independent variable in explaining the dependent variable. So these are like correlations. Okay, next we come on to the canonical discriminant function coefficients. As I said, these are standardized, which I just explained. Now these are unstandardized discriminant function coefficients. Yeah, so we are here. So these unstandardized discriminant function coefficients are nothing but betas on your multiple regression. Now these are the betas which you get just by employing regression, just like that. But those standardized ones were those which were standardized, okay, using this variance. So they were put on a common footing. But these are unstandardized, these are raw, okay. So it is now indicating what? So what are these unstandardized scores? So these can be interpreted as the multiple regression coefficient betas, and they're going to tell us unique contribution of independent variables to the discriminant function. So they provide information on the relative importance of each independent variable. Just like your standardized coefficients did, they're also going to do the same job. Okay, so the higher value means more important is that independent variable. Now let's see what is happening. Durability has a 0.056, which is the highest, then 0.026 with performance, then 0.03 with looking. Okay, so that indicates the order in which it is desirable, the independent variables are desirable or more important to your analysis. Now, actually, this is the point at which we are going to make our discriminant function. The di is equal to alpha plus beta 1 x plus beta 2 x2. So that is the point that now this will help us to make the discriminant function. And your discriminant function is going to look like this. Di is equal to the intercept, that is the constant here, minus 3.021 plus 0.056 into durability as an independent variable plus 0.026 into performance as an independent variable minus 0.03 into looking as an independent variable. So this is the discriminant function which we have been looking for, and this function will become our guiding light in classifying the cases. Okay, so once you have this function, you can go about the classification. Okay, now I'm going to stop this video up until the discussion of this function by reiterating that these coefficients will make the discriminant function in the fashion that di, that is the discriminant function score, is equal to minus 3.021 plus 0.056 into durability plus 0.026 into performance minus 0.03 into looking of the bike. Now, keeping in mind this particular knowledge of discriminant function, we will be able to look at the classification that I'm going to reserve for the next lecture. Thank you for watching the video.